Hello. So we can start today. Uh, so our topic today is the calculation of eigenvalues and eigenvectors. Eigenvalues and eigenvectors. Eigenvalues and eigenvectors are quite important in the many engineering applications. So the calculation for them and understanding their mechanism is very important. So I briefly started this topic in the last lecture. So we say that eigenvalue is observed when we have a square matrix A, and if that square matrix is then multiplied with a vector, that is a column vector, and that column vector is such a vector that when you multiply it by A, then we get this again a column vector, but that column vector can be a multiple of that number. Okay, so with a multiple of that number. So AU is equal to lambda U. So that means where A is a matrix, U is a matrix, U is a vector, which is a special form of a column matrix, and lambda is a scalar or just a number. It can be a real number or it can be even a complex number as well. So we gradually, so this means that if we have this matrix A, then by some of the methods, we can find the vector and this number. So this vector is called as the eigenvector, and this corresponding number is called as the eigenvalue. So we verified with one example. So let's do one more example. Suppose if A is equal to, A is a matrix. A is a matrix which is equal to minus 7, 10, 5, minus 7, 10, minus 5, 8. And U is a vector or a column matrix. Okay, U is a vector 2, 1. So verify that U is a eigenvector. So if we want to verify it, so then we will multiply A with U. So matrix multiplication, minus 7, 10, minus 5, 8, 2, 1. And then we will find its multiplication. So it will be minus 14 plus 10. It will be minus 10 plus 8. So from the matrix multiplication, we find it is minus 4 and minus 2. So minus 4, from minus 4, minus 2, we can take a common multiple of minus 2. Okay, so inside it will be 2, 1. So now this is 2, 1 is the same matrix as U. So we can write it like minus 2 is this. And then we can replace this vector 2, 1 by U. So in this case, what we have found that we have met the condition AU is equal to lambda U. So where lambda is equal to minus 2. So the eigenvalue, lambda is the eigenvalue. So lambda, so the eigenvalue for this combination is minus 2. So therefore, in this case, we have just verified it, okay? Later on, we will find, we will learn a method that if we just have been given this matrix A, then can we find the vector and its value, eigenvalue. Okay, so in this case, we have verified it, okay? So that this is the vector and this is the matrix, and this is the eigenvector, and this is the eigenvalue. So this was the 2 by 2 case. Let's see another example by 3 by 3 matrix, or 3 by 3 matrix. Suppose if matrix A is 10, 12, minus 6, 10, 12, minus 6, and then 8, 11, minus 4, 8, 11, minus 4, and then 34, 44, minus 19. 34, 44, minus 19. And suppose that the U matrix is, that is the vector is 0, 1, 2, 0, 1, 2. So if we want to verify it, that U is an eigenvector, so again we can multiply. So AU will be 10 times 0 will be 0, 12 times 1 will be 12, minus 6 times 2 will be minus 12. So 8 times 0 will be 0, 11 times 1 will be plus 11, and then minus 4 times 2 is minus 8. And then 34 times 0 is 0, 44 times 1 is plus 44, minus 19 times 2 is minus 38. So what we get is, this is 0, this is 3, this is 6. So now from here we can take 3 as common. So if we can take 3 as common, so this will still be 0, this will be 1, this will be 2. So what is 0, 1, 2? 0, 1, 2 is vector U. So it means that we can write it like 3 times U. So in this case, U is a eigenvector, and the eigenvalue is 3. So eigenvalue is 3. So remember that this type of thing is not possible with every vector. So eigenvector, every vector is not an eigenvector for some given matrix. So for some given matrix, there are some specific eigenvectors and eigenvalues, okay? So with this thing in mind, so then we can solve some more examples. Okay, so now the question is, if we have some matrix, if we know some matrix, then how to find the eigenvalue and eigenvector. So in this, here we have just verified it, okay? So question is, if given that is given a matrix, and it has to be a square matrix, okay? Given a matrix, then how to find find the corresponding eigenvalue, eigenvectors, and eigenvalue, okay? So this is the question. So so now for this purpose, we will need to use the determinants, okay? That means that, so that's why we studied the determinant before this topic, okay? So we need to know how to find the determinants so that we can determine the eigenvalues and the eigenvector. Okay, so for the eigenvectors, there is a relationship which holds true, and that relationship is called as the determinant of this given matrix A minus the eigenvalue times the identity matrix, okay, is equal to 0, So this is the relationship which holds true for the eigenvalues and eigenvectors. So this can be also proved, and that has been, the proof has been done in the book, but we will not go for the proof over here. So that we need to know, and then we need to understand, or we can apply this relationship. So if we take, if we know a matrix A, and then we subtract from that matrix lambda times the identity matrix, and then if we take the determinant of that, and that determinant should be equal to 0. So using this relationship, then we can find the eigenvalue first. So first of all, then we will find the eigenvalues, and from the eigenvalues, then we will find the eigenvectors. Okay, so this is the basic relationship which you need to remember. Okay, determinant of A minus lambda times the identity matrix is equal to 0. And then for the definition of the eigenvalue, so you need to know this relationship. So only these things you need to know, and then I think you can solve most of the eigenvalue problems. Do you have any question?
No.
So let's apply this relationship. Okay, so for example, if we know that A is a matrix like 3, 1, 1, 3. So find the corresponding eigenvalues and eigenvectors. Okay, so find the eigenvalue and eigenvector. Okay, so find eigenvalue and eigenvector. That is the find lambda and u. So you know that lambda is eigenvalue and u is the eigenvector corresponding. So we have this 3, 1, 1, 3. So for this, if we want to find the lambda and u, so first of all we will find the lambda, that is the eigenvalue, and then from there we will find the eigenvector, and then of course later on even we can verify it. So remember the basic relationship, which is called as the determinant of A minus lambda I is equal to 0. Okay. In this case, this I is the identity matrix. Okay, I is the identity matrix. So I2 is actually 1, 0, 0, 1. So in this case, since we are using the 2 by 2 matrix, so we will use I2. Okay. If, for example, if we will be having a 3 by 3 matrix, so then we will be using I3. So it will be 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. And in this relationship, this A minus lambda I, this is called the characteristic equation. Characteristic equation. Okay, it is called as the characteristic equation. So, so if the question is find the characteristic equation for this, with determinant. Okay, determinant of A minus lambda I is called as the characteristic equation without 0. Okay, without 0. So that is called as the characteristic. Okay, sorry. It is, in fact, I just mixed up the things. Yeah, in fact, the determinant of A minus lambda I is equal to 0. That is the characteristic. That will be the characteristic equation. In this case, because lambda will be an unknown, lambda will be an unknown quantity. Okay, so that characteristic equation will be in terms of the powers of lambda. Okay, so that is be called as the characteristic equation, and the solution of this characteristic equation will be the eigenvalues. Okay, so the solution of this characteristic equation will give the eigenvalues. Anyway, so with this brief introduction, so let's find a minus lambda I first. So a is 3 and 1 3 1 1 3 3 1 1 3 and minus lambda, and then I in this case we will use I2, so it will be 1 0 0 1. So what will be this? This will be then how you can write it. So 3 1 1 3 and minus that will be lambda 0 0 lambda. Okay, and then it will be now 3 minus lambda. Okay, 3 minus lambda, and then it will be 1 1 and 3 minus lambda. Okay, 3 minus lambda. So this is the a minus lambda I. So what is the determinant of a minus lambda I? So the determinant of a minus lambda I, since this is a 2 by 2 matrix, so the determinant will be this term multiplied by this term minus this term multiplied by this term. So it will be 3 minus lambda square minus 1 square. So if we will simplify it, then it will be 9 minus 6 lambda plus lambda square minus 1. So it will be 8 minus 6 lambda plus lambda square. So the characteristic equation is, okay, characteristic equation CE will be then lambda square minus 6 lambda plus 8 is equal to 0. So this is the characteristic equation. So now this is the quadratic equation, so we can easily solve it by any method you feel comfortable. So this can be easily factorized. So it will be delta and lambda square minus 4 lambda minus 2 lambda plus 8. Okay, so it will be lambda into lambda minus 4 minus 2 into lambda minus 4. So it will be lambda minus 2 into lambda minus 4 is equal to 0. So the solutions are then lambda 1 is equal to 2 and lambda 2 is equal to 4, or you can even say lambda 1 is equal to 4, lambda 2 is equal to 2. Anyway, so lambda 1 is equal to 2, lambda 2 is equal to 4. So these are the corresponding eigen values. Okay, these are the corresponding eigen values. So from these eigenvalues, we need to find the eigenvectors. Okay, so for the eigenvectors, we know the relationship is this: AU is equal to lambda U. Okay, and how we can solve for U from here? So we can take first one lambda value, and then we will solve this equation. So actually now we can do it like this. So you can write it like this: AU minus lambda U is equal to 0. Okay, where 0 is the zero matrix. Okay, in this case, to make it more to make it compatible with each other, because A is a 2 by 2 matrix. Okay, and but U is a 2 by 1 matrix. So this will not be compatible. Okay, this will not be compatible. So in this case, what you can do is we can write I times U is equal to U. Okay, can we write I times U is equal to U? So for example, if I is an identity matrix 1 0 0 1, and U is a matrix like U1 U2. So if we multiply it, then what will we get? U1 plus 0, and then it will be 0 plus u2. So basically we will get u1, u2, okay, which is same as u. So it means that we can write it like this, okay. So in other words, what we can do is we can write it like this: a u minus, sorry. So we can write it like a u minus lambda I u is equal to 0. Or we can write it like a minus lambda I times u. We can even write like this, because now in this case, A is a 2 by 2 matrix, lambda I will be a 2 by 2 matrix as well. So this is now a system of the equations, okay, system of equations. So we can solve it by the Gauss elimination method, okay, by this system of the equation. So which means that what we have to determine is A minus lambda I, and the solution of that for this homogeneous solution, because on this side it will be 0, 0. Solution of that homogeneous solution will be the eigenvector. So this means that from this lambda value, from each of these lambda value, we need to determine this solution. Okay, so then we know that A was what? A was 3, 1, 1, 3, and lambda 1 was 2, lambda 2 was 4. Okay, lambda 2 was 4. So what is A minus lambda 1 u, sorry, lambda 1 I, sorry. No. So we need to find A minus lambda 1 I is equal to 0, that solution of this system. Okay, so in this case, then what we can do is 3, 1, 1, 3, and minus lambda 1 was 2, and then 1, 0, 0, 1. Okay, so what is this now? It will be now 3 minus 2 is 1, and that will be 1, and then 1 minus 0 will be 0, and then it will be 3 minus 2, that will be 1. So we will get this 1, 1, 0, 1, this matrix. And on this right hand side, we have 0. That means we have a for the augmented matrix, augmented form. In the augmented form,
it's 1 minus 0 is 1.
Wait a minute. Sorry, 3 minus, okay, 3 minus 2 is 1, okay? 1 minus 0 is 1, and then 1 minus 0 is 1. Yes, correct. It's 1. And then 3 minus 2 is also 1. So it is 1, 1, 1, 1. Okay, so the augmented matrix is augmented form. It will be 1, 1, 1, 1, and sorry, okay, I make a mistake. And then 0, 0. Okay, so this is the augmented form. So this augmented form will be now 1, 1, 0, and then this will be 0, 0, 0. Okay, so we should get a solution from here. So if we take the variables as like u1, u2, so from the second equation, with nothing we get. So from the first equation, we get u1 plus u2 is equal to 0. So u1 is equal to minus u2. Or if we take u2 as equal to s. So it will be u1 will be equal to minus s. Okay, so the solution is in this case u1 u2, so that will be minus s and s. Okay, or if you take s as common, so it will be minus 1 and 1. So this minus 1 and 1, s is just a general numbers, okay, as an arbitrary constant. So this minus 1 and 1 is the eigenvector. So minus 1 and 1 is the eigenvector. Okay, so we can verify it. So whether our answer is correct or not. So 3, 1, 1, 3 times minus 1, 1. So it will be 3 into minus 1 is minus 3. 1 into 1 is 1. And then 1 into minus 1 is minus 1. 3 into 1 is plus 3. So what we get is minus 2 and 2. So if we take 2 as common, okay, so what we get is minus 1 and 1. So which is then 2 times u. Minus 1 and 1 is eigenvectors is 2. And 2 and the eigenvalue is 2, which is basically the same. So it means that our answer is correct. So this is the verification. This is the verification. Okay, 2 times u. So similarly, we can find the eigenvector corresponding to the second eigenvector. So I leave it for you to find it and verify it. Okay. Is there any question regarding this calculation?
On the previous lesson, we saw the same equation, but we got another eigenvector. Okay.
Another eigenvector? Mm-hmm.
Yeah, it was 1 and 1. So I'm a little bit confused.
1, 3, and then the other eigenvector is 1 and 1. So maybe that is corresponding to the eigenvalue of 4. Is it?
So it actually can happen.
Yes.
Yeah. Is it that in that case we found that the eigenvalue was 4. Yes, in that case we found that the eigenvalue was 4. So 4. So the the other eigenvector 1 you will get for this eigenvalue. Okay.
Okay.
Okay. Next, we can do one more example. Okay, for a 3 by 3 case, let's do it for a 3 by 3 case. So 3 by 3 matrix. A is 1, 0, minus 2, 0, 1, 2, 2, 2, 1. 2, 2, 1. Okay, so if we have a 3 by 3 matrix and we want to find its eigenvalue and eigenvector, so the shortcut ways, okay, because earlier I just explained and did something like for the explanation I wrote those equations. So for writing the for finding the determinant, what we can do is we can find it like what we will do is we will subtract lambda from the diagonal members. So if we will, for example, if we say like a minus lambda I, so the final result will be that the only change will be in the diagonal element. So it will be 1 minus lambda, 0 minus 2, and will be 0, 1 minus lambda 2, and then 2, 2, 1 minus lambda. Okay. And now we can find its determinant. So for finding its determinant, so we will expand from the first row. So it will be 1 minus lambda times the determinant of this minor matrix. So 1 minus lambda 2, 2, 1 minus lambda. And the second term, which is 0 over here, so therefore we will just put it like 0. And then over here, so it is the signs will change like plus, minus, plus. So it will be plus sign, so that is minus 2 is already over here. And its minor matrix will be 0, 1 minus lambda, 2, 2. Okay, so now we get 1 minus lambda, and then its determinant will be 1 minus lambda square. So it will be 1 minus 2 lambda plus lambda square and minus 4. And then minus 2, its determinant will be 0 times 2 is 0 minus 2 times of 1 minus lambda. Okay. So if we need to simplify it, so if we will simplify it, then what we will get is we will get in this case, after simplification, okay, I will not do this algebra over here, but it's not, it's very easy actually. So we will get, what we will get is minus lambda cube minus 3 lambda square plus 3 lambda and minus 1 equal to 0. Yeah, so this will be, and if we take it equal to 0, so then we will get lambda cube minus 3 lambda square minus 3, plus 3 lambda minus 1 equal to 0. So this will be the characteristic equation which we will get. So in fact, in this case, the values were very cleverly selected so that we can find a nice solution for this cubic equation, cubic polynomial equation. So in this case, in this cubic equation, there is this nice solution because this is a complete cube of lambda 1, lambda minus 1 cube. So lambda cube minus 3 lambda square plus 3 lambda minus 1, if you remember from your algebra knowledge. So this is the cube of lambda minus 1 cube. So in this case, therefore, the value of lambda will be 1. So since this has a cubic equation, it should have 3 roots. But in this case, incidentally, all the 3 roots are the same. So therefore, there is only one eigenvalue in this case. Okay. So for finding the eigenvector, what we will do is we will find it by the previous method. So we will find a minus lambda I as usual. So what is a minus lambda I? In this case, we can directly find from here because lambda will be 1 minus lambda. Lambda is 1. So the augmented matrix will become, so this will be 1 minus lambda will be 0. So it will be 0, 0 minus 2. And then it will be 0, 0, 2. And then it will become 2, 2, 0. And then its augmented matrix will be 0, 0, 0. Okay, so for this system, what we can do is, in this case, this system is, we can find the solution by forward substitution. Okay, So for example, if we take the first equation, okay, if we take the first equation, so it will be minus 2u. So if we take like the components of u as u1, u2, u3, so it will be minus 2, u3 is equal to 0. So u3 will be equal to 0 in this case. And then from the second equation, what we get is, we also get the same, right? 2u3 is equal to 0. So u3 will be equal to 0. Actually we get u1, u3 as 0. So from the last equation, what we get is 2u1 plus 2u2 is equal to 0. So in this case, we will take maybe, we can take u2 as equal to s. So from here we get u1 is equal to minus s. Okay, u1 is equal to minus s. So therefore our u matrix will be minus s, s and 0, minus s, s and 0, or if we take s as common, so it will be minus 1, 1 and 0. So you can even say, because it is an arbitrary constant, we can even say like 1 minus 1, 0. So that is also correct, okay? Because we can take minus 1 as common as well. So from that is no problem. And then that minus 1 is absorbed into this arbitrary constant. So so therefore the eigenvector is minus 1, 1, 0. And then we can verify it. So we have matrix A as 1, 0, minus 2, 0, 1, 2, 2, 2, 1, and times minus 1, 1, 0. Okay. So then what we will get is 1 into minus 1 is minus 1, 0, and that will be 0. Minus, that will be 0 again. And this is 0, then that is 1, and that is 0. And then the last one will be minus 2, then plus 2, and then 0. So what I will get is minus 1, 1, and then 0, which is the same as the eigenvector. And in this case, the eigenvalue is 1, okay? So that means we have already, we can verify it, verification. So we have verified that our eigenvector is the correct one. Okay, so this is this is how we find the eigenvalues and eigenvectors. So do you have any questions regarding this?
No questions.
No questions. Okay. Okay, so that is okay. So let's do one more question. So suppose if we have a matrix A as 2, 0, 0, 9, minus 1, 3, and 6, minus 2, 4. And its eigenvalue, one of the eigenvalue is given as 1. Okay. So what we need to do is find a basis for the eigenspace of A associated to the given for these conditions. So here we are using the word eigenspace. Eigenspace is nothing but the set of vectors, set of eigenvectors, okay, for corresponding to this A, okay. So, but we need to find the basis for the eigenspace, okay. So in this case, what you will do is you will write the equation, write it into the augmented form. So for finding the basis, what you will observe is that the eigenspace of this given system will be the solution of the homogeneous system. Okay, it will be the solution of the homogeneous system, because in this case we will see that the system is something like this: A minus, this is the equation which we use. Okay, so this is the homogeneous system of this equation. Remember that a homogeneous system is that in which all the terms are zero on the right hand side. Okay, so for this homogeneous system, if we find the solution, that solution will be the eigenspace, and from that eigenspace we can find the basis. So in this case, lambda is equal to 1. That means we don't need to find, it is already given. So we find A minus lambda I. So what is the effect of A minus lambda I? The terms on the diagonal will change. Only the terms on the diagonal will change. So therefore, A minus lambda I will become 2 minus 1 is 1, 0, 0. And then it will be 9 minus 2, 3. And then it will be 6 minus 2, and then 3. Okay, so for finding its eigenspace, then we write it in the augmented matrix form. So the right hand side terms are all 0. So this is the augmented matrix, and now we apply the row operations to make it into the echelon form. Okay, to convert them into the echelon form. Remember that in the previous case, here you can see that I did not convert it into the echelon form, but rather I just find the solution directly. So we can even convert it into the echelon form as well. So for this purpose, we will need to interchange these rows. From this row will come over here, and then the other row will come over here. So there will be actually no difference in the solutions in any ways. But here I just use the direct method. So, but the standard way is to convert those augmented matrix into the echelon form. So in this case, we can get a nice echelon form like this. So 1, 0, 0, 0. And then it is 9. So what I will be doing is 9 minus 9, that is 0, minus 2, then it will be minus 2, then it will be 3. Nothing is going to be changed except the first term. And then over here, it will be 0, then it will be, because all of these things are 0, so it is minus 2, 3, 0. So what I have done is I applied the row operation minus 9R1 plus R2. And now you know already that how these row operations are working, okay? And then from the second and third term, what you will get is 1, 0, 0, 0, and then 0, minus 2, 3, and then what you get is 0, 0, 0, 0 over here. Because in this case, what we did is minus R2 plus R3, that is R3. So the third row is all 0 in this case. So what actually we get is, now this was U1, this is U2, this is U3. So from the first equation, what I get is U1 is equal to 0, okay, from the first equation. And from the second equation, what I get is minus 2U2 plus 3U3 is equal to 0. So in this case, what I get is U2 is equal to 3 by 2 U3. So if I take U3 as equal to S, so it will be 3 by 2 S. Okay. So U2 will be 3 by 2 S. So therefore, U vector will be, the eigenvector will be 0, 3 by 2 S, and then S. If we take S as common, and although it is not necessary, but we can remove its fractions by multiplying all the terms by 2, and then that 2 will be absorbed into this arbitrary constant. So it will be 2s. So 2s will be still s. So instead of 0, 3 by 2s, I can write 0, 3, and 2. Okay. So I have removed the fractions from the answers, from the answer. So then in this case, this is our answer. So we will say that a basis for the eigenspace associated to given eigenvalue 1 is, for this given eigenvalue, the associated the basis is this. So it will be represented in the form of a set. So it will be a set of a matrix, single set, 0, 3, 2, and then this is closed. Okay, so this will be the answer for the basis. So in reality, we have performed the same calculation which we have done for finding the eigenvalue and eigenvector. Okay. There is one more example, but we have almost run out of the time. So in any way, I mean, the main part of this type of the topic is actually completed. That one example which I wanted to show over here, then I can do it in the next class on Monday.